point A, remember it's not moving, so it's all potential energy, is equal to point C, which now has no height, it's all kinetic energy. Alright, so EP at A is going to be mgh for A is equal to 1/2 mv at point C squared. Alright, the mass is in both terms, cancels out, so we just need to rearrange and solve for velocity. When you rearrange, the velocity of C is going to be equal to the square root of 2 times gravity times the height of A. And now all we're going to do is plug in and solve. Square root of 2 times 9.81 meters per second squared times the height of A is not 12 meters, but it is 8 meters. So it's equal to 8.0 meters. This is going to give us a velocity of 12.5 meters per second. Alright, if you don't understand doing it this way, go ahead and try doing it the same way we did for point B. See how you make out. See what you get. See if you get the same answer as me. The last question in this wants us to determine the speed of the roller coaster at the lowest point if it had a speed of 8 meters per second when it left point A. So now, at point A, you start with an initial speed. So your mechanical energy at point A is going to be equal to your mechanical energy at point, its lowest point, which we labeled point B. So you're going to have potential energy and kinetic energy, because now you have an initial speed, is equal to the potential energy plus the kinetic energy. Alright, make sure you're labeling what point you're at. I'm going to leave this for you to try on your own, see how you do, and see what you get for an answer. My hint to you, or I guess the answer for this one that I got, is I got a velocity that is equal to 16.1 meters per second. See if you can get the same thing as me. In this final example, we are going to go ahead and use all of our types of energy that we've learned in this lesson. So we have a 3 kilogram block, starts from rest at a certain height on the rack, relative to the ground, and slides down. It is found to have a speed of 3 meters per second when it collides with a stationary spring bumper that is fixed at one end. The spring has a constant of 375 newtons per meter. Assume an isolated system. So remember, now we don't need to worry about anything about air resistance, friction, any of those external forces. But we want to list the types of energies at point A, B, and C. So at point A, it tells us that it starts from rest. It is not moving. Because there's no movement, there's no kinetic energy. But it does have a height relative to the ground. So it still has potential energy. Alright, point B right here is now on ground level, and the block has slid down and there's no more height. Alright, there's still a velocity, so we're going to have kinetic energy, but because we're at ground level, there's no height, we have no potential energy. So B is going to be all kinetic energy. And finally, at point C, we are going to hit this spring, and at this spring, it's going to go ahead and stop. Right? It's going to go ahead and compress and stop. Because there's no movement, there's no more kinetic energy. There's also no height, so there's no gravitational potential energy. But we have a spring constant. We have a spring that's compressed. Because that spring's compressed, we have elastic potential energy. Alright, so the next part of the question wants us to determine how much the block compresses the spring. So at point C, how much is the spring being compressed? We want to determine at that point what is X. In the question, it tells us the spring constant is 375 newtons per meter. It tells us that it collides with the speed of 3.00 meters per second squared, and that the block has a mass of 3.0 kilograms. So using our conservation of mechanical energy, we know the mechanical energy at one point is going to be equal to the mechanical energy at another point. So let's look at point B, where we have all kinetic energy, and point C, where we're going to find out what our spring compression is. So at point B, it is all kinetic energy, and at point C, it's all elastic potential energy. For your kinetic energy, you have 1/2 mv squared is equal to 1/2 kx squared. We have 1/2 on both sides, so that will cancel out. And we're going to rearrange and solve for x. So x is equal to the square root of mv squared over k. We know mass, we know velocity, and we know the spring constant. So we can plug in and solve for x. The mass, 3.0 kilograms, times the speed, 3.00 meters per second squared, divided by the spring constant, 375 newtons per meter. And we're going to take the square root of all of that. When you plug that in, it's going to give you an answer of 0.268 meters, or that's also equal to 27 centimeters. Alright, last part of the question wants us to determine what is the block's release height. So how high is it when it's at point A relative to the ground? So again, at point A, it starts at rest. So your mechanical energy at point A is going to be equal to nothing but potential energy. Alright, we're going to make that equal to, we can take either point, we can take point B or point C. I'm going to pick point B. So the mechanical energy at point B, remember, was all kinetic energy. Alright, there was no height and there was no springs. So that's going to be equal to all kinetic energy. So we have mgh is equal to 1/2 mv squared. We can cancel out mass because it's in both terms. We know g is 9.81 meters per second squared. We want to find what is h, and we found in the last question, in the question it tells us that our velocity is 3.0 meters per second squared. So if we rearrange for h is equal to 1/2 v squared over g, and that's equal to 1/2 times 3.00 meters per second squared over 9.81 meters per second squared. When you plug this in and solve, you're going to find it has a height of 0.46 meters. Alright, I went through this very quickly. The entire unit got done in one lesson. A lot of this is review from Science 10. If you are struggling with it, if you need help, please let me know. If you are doing well, that's awesome, and you can continue moving on. Alright, best of luck.